So let's take a look at this problem together. There's a couple tricky spots on it that I want to make sure that we clarify, just in case you're having some problems. The question asks, an object is dropped from an altitude of 1 Earth radius above the Earth's surface. If m is the mass of the Earth and r is the radius, its radius, the speed of the object just before it hits the Earth is what? So, like always, I'm going to draw my picture. I know that this is 1 Earth radius to get to the Earth's surface, and I'm actually dropping a mass. I'm going to call it little m, where big M is the mass of the Earth. Little m is going to fall a distance of, again, 1 Earth radii down, a radius down. Well, I look at this problem, and it looks to me like I'm dropping an object from a height. It's going to hit the ground. It's dropping from rest. My initial velocity is equal to 0, and I want to know what its final velocity is. To me, this looks really a lot like conservation of energy problem. K initial plus U initial is equal to K final plus U final. Normally, when I get to this point that I have to set my potential energy to be 0 somewhere. Well, I'm going to look at this and know that I'm at a large distance away from the Earth, or a significant distance away from the Earth, which means that I want to use universal gravity. When I use universal gravity, potential energy due to universal gravity is going to be g m1 m2 over r12 over r12, and there's a minus sign in there. This assumes that at infinity my potential energy goes to 0. I don't get a chance to really set it. So infinity is going to give me a potential energy of 0 at a distance equal to infinity away from the Earth's center. It's just the convention that we use. This is just something that's built into universal gravity. So let's go through it like we normally do. We're just going to add up all of our initials, add up all of our finals, and see what we get. So I have 1/2 mv initial squared minus gm Earth, mass of the object, over my initial height squared, which is 2re quantity squared, is equal to 1/2 little m v final squared minus g big M of Earth little m over re. And that value is not squared. I'm dealing with gravity, the potential energy of gravity, not the force. It's a common mistake to make. You just watched me make it, but was looking at my units, and my units didn't work out. So I go through this problem now, and I start to look at it, and I go, well, my v initial is 0. And I notice that I have a common factor of little m in every one of these equations. So I get g me over 2re is equal to 1/2 v final squared minus g me over re. Move this to the other side and get a common factor out, which gives me g me over re times the quantity. I get 1 factor moving over to the other side of that, minus a 1/2 factor on the other side, and this gives me 1/2 v final squared. So g me over re, this is a factor of 1/2. That cancels with that 1/2. It's going to be v final, and I'll take the square root of it. So when I get to the end, it's going at a speed of gm over r. So I have value a as it's labeled for me. Just to make a check to make sure that my subscripts worked right, I had a 1/2 factor of this gm over r. I had a factor of gm over r, which gave me a factor of 1/2 gm over r when everything was said and done. That canceled with my 1/2 from my 1/2 mv squared. Looks like my coefficients worked, and I get this answer. So we solved this exactly like we did a normal drop an object from rest down to the ground. It's just that we used a different form of our potential energy, making sure that every time we did it, we referenced off the same potential energy 0 at infinity. So we had to take into account both of the distances from the Earth's center.